Hi everyone, this is Srikanth, Assistant Professor of EEE Department. In this session, I am going to discuss the problems on diodes and diode rectifiers. Here, an AC voltage of peak value of 20 volts is connected in series with a silicon diode and a load resistance of 500 ohms. If the forward resistance of the diode is 10 ohms, find the peak current through the diode and peak output voltage. What will be these values if the diode is assumed to be ideal? So here the peak input voltage is 20 volts, forward resistance is 10 ohms, load resistance is 500 ohms, potential barrier is 0.7 volts. Now our circuit will become, this is the V input, that is 20 volts, V output across the diode is 0.7, 10 ohms and 500. Here the peak current through the diode will occur at the instant when the voltage reaches the positive peak. V input is equals to Vf is equals to 20 volts. So here Vf is equals to V0 plus I peak into Rf plus RL, where If peak is equals to Vf minus V0 by Vf minus V0 by Rf plus Ra. Here Vf value is 20 volts. Here the Vf value is 20 volts and V0 value is 0.7. 20 minus 0.7 by 10 plus 500, which will gives us the value as 37.8 milliamperes. And peak output voltage IF peak is into RL is equals to 37.8 milliamperes into 500 ohms, which is equals to 18.9 volts. The ideal diode case, if we take the RF value is 0, that is we need to place V0 value as 0. So if Vf is equals to IF peak into RL, where IF peak is equals to Vf by RL, that is 20 by 500 ohms, which is equals to 40 milliamperes. Here the peak output voltage is equals to IF peak into RL is equals to 40 into 500 ohms, that is equals to 20 volts. Now find the current through the diode in the circuit shown in figure. Assume the diode to be ideal. Here the 10 volts input is given. R1 value is 50 ohms. R2 value is 5 ohms. We need to calculate the current flowing through the diode. Here the diode, when it is forward bias, diode is short circuit. When the diode is short circuit, there is no R2 resistance. So E0 is equals to Thevenin voltage, that is open circuited voltage across AB. When the diode removed, here R2 by R1 plus R2 into V, that is equal. Here E0 is equals to R2 by R1 plus R2 into V, which is equals to 5 by 50 plus 5 into 10, which is equals to 0.909 volts. Where R0 is equals to Thevenin resistance, the resistance across the AB with the diode removed. Here the battery replaced by a short circuit, that is R1 R2 by R1 plus R2, that is 50 into 5 by 50 plus 5, that is 4.55. Here the output voltage is 0.909, that is Thevenin voltage, and Thevenin resistance is 4.55. Now the current through the diode is equals to E0 by R0, that is 0.909 by 4.55 which is 0.2 milliampere. Sorry, 0.2 amperes, which will gives us 200 milliamperes. Now calculate the current through 48 ohm resistance in the circuit shown in figure. Assume the diodes to be silicon and forward resistance of each diode is 1 ohm. Here, this is the 10 volt source D1, D2, D3, D4. Here 10 volt source D1 D1 and D3 are going to conduct. When D1, D3 are going to conduct, the resistance of 1 ohm and 0.7 volts are connected in series with the circuit. Now the net circuit voltage is 10 minus 0.7 minus 0.7, which is 8.6 volts. There is a voltage drop because of the resistances. The total circuit resistance is 1 plus 48 plus 1, which is equals to 50 ohms. The short circuit current, which is equals to 8.6 by 50, that is 0.172 amperes, which is equals to 172 milliamperes. The next problem is determine the current in the circuit shown in figure. Assume the diodes to be silicon and forward resistance of the diodes, which is to be 0. Here the diodes are of silicon diodes and forward resistance of the diodes is given as 0. So here when it is forward bias, only there will be a 0.7 volts drop will be there, but the resistance, forward resistance is 0. So here the E1 value is 24 and resistance value is 2 kilo ohms and E2 value is 4 volts. Here I is equals to E1 minus E2 minus V0 by R, which is equals to 24 minus 4 minus 0.7 by 2 kilo ohms, that is 19.3 volts by 2 kilo ohms, which is equals to 9.65 milliamperes. Now find VQ and ID in the network shown in figure. Use simplified model. Here is the 10 volts and we have to calculate VQ and ID, current flowing through the diodes. Here by applying Kirchhoff's law to the closed circuit of ABCD. So minus 0.7 minus ID into 2 minus 2 into ID plus 10, which is equals to 0. Here 6 ID is equals to 9.3, where ID is equals to 9.3 by 6, which is equals to 1.55 milliamperes. Where VQ is equals to 2 into ID into 2 kilo ohms, which is equals to 2 into 1.55 milliamperes into 2 kilo ohms, that is equals to 6.2 volts. Determine the currents I1, I2 and I3 for the network shown in figure. Use the simplified model for the diodes. Here the diodes are considered as silicon diodes. Here the diodes are replaced with only 0.7 volts and there is no diode resistance which is given. So here in order to calculate I1, I2, I3, we have to proceed with the KVLs. Here the voltage across R2 is equals to 0.7. Voltage across R2 is only 0.7. So I2 is equals to R2 by V2 by 3.3 kilo ohms, that is 0.212. By applying Kirchhoff's voltage law to loop ABCDA in figure 8.2, we have minus 0.7 minus 0.7 minus I1 into R1 plus 20 equals to 0, where I1 is equals to 18.6 by 5.6 kilo ohms, that is equals to 3.32 milliamperes, where I1 is equals to I2 plus I3, where I3 is equals to I1 minus I2. From this we will get it as 3.10H. Determine if the diode in the figure is forward bias or reverse bias. When the diode is forward bias and reverse bias, that is short circuit and open circuit. So let us assume that 9.1 is off, that is a reverse bias. In the reverse bias condition, circuit become 9.2, that is here the voltage will be divided across the two series connected elements. So V1 is equals to 10 by 2 kilo ohms into 8 kilo ohms into 8 kilo ohms, that is equals to 8 volts. And V2 is equals to 10 volts by 4 kilo ohms into plus 6 kilo ohms, that is equals to 6 kilo ohms, that is equals to 6 volts. Now the voltage across diode is equals to V1 minus V2, that is 2. Now V1 minus V2 is equals to 2 volts is enough the voltage to make the diode forward bias. Therefore, our initial assumption was wrong and the diode is forward bias. Determine the state of the diode for the circuit shown in figure 10 and find ID and VD. Assume simplified model for the diode. Here, the diode which is connected in parallel with the 1 kilo ohm, and here it is a silicon diode, so the diode will be replaced with the 0.7 volts. Now let us assume that the diode is on, therefore we can place the diode with 0.7 volts battery, which is referring to above figure 2. We have, if we see from this circuit, here I1 is equals to here the input voltage is 2 volts and the other side we are having the voltage of 0.7. So 2 minus 0.7 by 4 kilo ohms. 2 minus 0.7 by 4 kilo ohms, that is 1.3 volts by 4 kilo ohms, that is 0.325 milliamperes. Now I2 is equals to 0.7 by 1 kilo ohms, which is equals to 0.7 milliamperes. Now ID is equals to I1 minus I2, that is 0.325 minus 0.7, which is equals to minus 0.375. Here, in order to analyze the circuit properly, we should replace the diode with an open circuit. The voltage across the diode is 2 by 1 kilo ohm plus 4 kilo ohm into 1 kilo ohm. We know that 0.7 volts is required to turn on the diode. Since VD only is 0.4 volts, the answer confirms that the diode is under off condition. In this session, we have discussed some different problems on diode circuits. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.